Hello, my name is Isabella and I will be your host today for another mathematics video brought to you by RJ. We have an exciting video for you today. Is there a prime number test function? More specifically, is there a closed prime number test function? This is a question that has baffled mathematicians, especially number theorists, since prime numbers were discovered. We may have an answer to this intriguing question by the end of the video. A factor of an integer n must be an integer between 1 and n. So, any factor of n is of this form where I ranges from 1 to n. Remember what I said about factors. They must be integers. So, how can we ensure this is an integer? We use the integer test function. We need I to scan through integers from 1 to n. This can be done using a summation. We know that the integer test function produces either a 0 or 1. Therefore, by using a summation, we obtain a function for the number of factors of n. In a previous video, I gave two definitions of a prime number. A prime number is a number that is only divisible by 1 and itself, and only has two factors. Clearly, whether or not n is prime, n is always divisible by 1 and n. So now, let's just ignore these two factors. We do so by subtracting 2. We are only concerned about the in-between factors. Note that this only works if n is greater than 1. As I said in the other video, n equals 1 is a special case, since 1 is neither prime nor composite. Now, it should be clear that the number of factors of n can never exceed n. I'll leave that to you to prove. Hence, the ratio of factors of n to n is at most 1. Moreover, the ratio of in between factors of n to n is between 0 and 1, not including 1. Again, I leave that to you to check. So let's divide this by n. We now have a function that produces a 0 if there are no in-between factors and a number between 0 and 1, not including 0 or 1 if there are in-between factors. Suppose we subtract this from 1. We now have a function that produces a 1 if there are no in-between factors and a number between 0 and 1, not including 0 or 1 if there are in-between factors. We want this number to equal 0 if there are in-between factors. So what can we do? We take the floor. We have a prime number test function. It looks crazy, doesn't it? This is not a closed formula because of this summation. So, is there a closed formula for the prime number test function? Let's look at Wilson's theorem. Wilson's theorem states that n minus 1 factorial is congruent to -1 mod n, if and only if n is prime. I'm not going to prove this. I'll leave it to you to do so. In fact, there are several ways to prove this, but let's look at a consequence of this. If n is prime, then none of these numbers cancel out with n. At the same time, if n is composite, then at least one of these numbers cancels out with n. What does this mean? It means that if n is prime, then this is not an integer. If n is composite, then this is an integer. I'm sure you all know what to do now. We use the non-integer test function. I derived this in the previous video. If you haven't watched it, I suggest watching it. This is great. However, there is one issue. Can you guess what it is? This doesn't work for a certain number. Do you know which one and why it doesn't work? The number is 4. The factorial expands to this in the numerator, and we have 4 in the denominator. We can express 4 as 2 times 2. One pair of 2's can cancel out. There is still 1 2 left over, but we know 4 is composite. So we need to make this an integer. How can we do that? We just need to multiply by the square root of 4. In fact, we can do this for any n. Of course, n may not always be a square, which means the square root of n might not be an integer. We need the numerator to be an integer. To make it an integer, we can just take the floor of the square root of n. Multiplying this by what we already have has no effect on the test function. The floor of the square root of n is just an extra copy of an integer in the factorial. So, if n is prime, we already know it doesn't cancel out. If n is composite, then, again, the floor of the square root of n is just an extra term in the product in the numerator, which still produces an integer. Now we have a closed formula for the prime number test function. It looks less intimidating than this version, right? I can now tell you if n is prime or composite. Of course, with large numbers, it might be easier with a computer because of the factorial, but this begs 2 questions. If we set these two equal to each other, can we derive a formula for this summation? This summation is essentially the integer counting function. And now that we have a prime number test function, can we derive a function that produces the nth prime? Are these 2 questions related? I hope you enjoyed the video. If you did and would like to see future videos, please like and subscribe. Also leave a comment telling RJ which areas of math you find interesting. Thank you for watching.